Welcome back, everyone. This is the third video in the Chapter 3 lessons. We're here on page 6 in the Chapter 3 lecture note outline, where we left off the last time, starting in section 4, which is about energy. As we learned in the first video, chemistry is the study of matter and the changes that matter undergoes. Now, those changes, the chemical and physical changes, are also accompanied by changes in energy. Those changes in energy can be subtle, like changes in temperature, or they can be quite dramatic, like explosions and emission of light. People have been fascinated by these changes for a very long time, and for good reason. These energy changes provided by chemical reactions can be harnessed and used for many valuable tasks, and they also give us special insights into the inner workings of chemical reactions. For example, take a look at this painting which depicts the discovery of the element phosphorus. Let me read to you an excerpt which describes this scene. One night in 1669, German physician Henning Brandt attempted to create the alchemical philosopher's stone. This elusive goal had been pursued by alchemists for centuries for good reason. It could transform, theoretically, base metals into gold. Brandt had spent most of his day in the laboratory heating a mixture of sand and charcoal with a tar-like substance that he produced by boiling down about 1,200 gallons of his own urine over a 2-week period. He then maintained the mixture at the highest temperature his furnace could reach. After many hours, a white vapor formed and condensed into thick drops that gleamed brightly for hours. This glowing, waxy substance had never been seen before. Brandt called it phosphorus. And this word, phosphorus, to describe this particular element, is pretty much a perfect name. This word phosphorus is from a Latin word that means the bringer of light. As an element, phosphorus is very well known for exhibiting this light-bringing behavior. For example, as a white powder, a small amount of friction will cause phosphorus to ignite into a glowing white flame. Other elements, like potassium, will burst into flame on contact with water. So let's take a look at this beaker, which has some pure potassium metal that was placed in it. Notice it has a purple flame. Other elements produce different colors. Strontium, for example, produces a very nice red color when it's passed through a flame. We're actually going to be learning about why different elements produce a certain spectrum of color when they're excited by things like heat and light. That's a little bit later. For now, let's start with learning the basics of how energy is involved in chemical and physical changes. So what exactly is energy? Well, let's try to keep our definition as simple as possible for now. Energy is a property that enables a substance or an object to perform work or to change temperature. We're going to see that energy can take many different types of forms. Things like mechanical energy, chemical energy, or nuclear energy. But regardless which form energy takes, energy is this stuff that can do things. And the things it can do include performing work and changing temperature. To help us get a better understanding of what energy is, let's look at 2 different types of energy. We can classify all energy as one of these 2 types. Energy can be kinetic energy or potential energy. Kinetic is a word that means movement, and it describes kinetic energy well. Kinetic energy is the type of energy that we get when things are moving around. We can say that kinetic energy is the energy of movement. Now, kinetic energy is different from potential energy. Whereas kinetic energy is the energy of movement, potential energy is stored energy. How does something store energy? Well, it stores energy based on its position. And it turns out its position can be in something called a field. So for example, if we have a ball on top of a hill, that ball has stored potential energy because of its position in a gravitational field. Soon we'll be learning about subatomic particles like electrons and protons. And those particles, which are charged magnetically, can be stored also in different places in electromagnetic fields. Because of their relative positions in these electromagnetic fields, we can store energy in those particles. So potential energy is stored energy, and kinetic energy is the energy of movement. We can convert potential energy into kinetic energy, and we can convert kinetic energy back into potential as well. For example, say we rolled this ball down the hill. Its stored potential energy is released as it travels through the field. That potential energy is converted into kinetic energy as a result. Now, one thing we always need to keep in mind is there are some guidelines about this transformation of types of energy. So when we convert kinetic into potential, or potential into kinetic, we have to follow something called the law of conservation of energy and mass. What this law states is that energy and mass can be transformed, but not created or destroyed. What this means is if we put, say, 100 grams of stuff into a reaction flask, and all that stuff reacts, at the end, we will still have to have 100 grams. We can't have less than 100 grams because matter cannot be destroyed, and we can't have more than 100 grams because matter can't be created. Matter, like energy, can only be transformed. However much we start with, we have to end up with the same amount at the end. So now that we've discussed the two different types of energy, kinetic energy and potential energy, let's go to the next page and look at some different examples. Energy can exist in various forms. For example, we're familiar with energy in the form of heat and mechanical energy. Every time we turn on a light bulb, we're using electrical energy. These are called forms of energy, and some of these forms are kinetic energy while others are potential energy. Let's go through these 6 and discuss their characteristics and see if we can classify them as potential or kinetic forms. The form of energy that we're probably most familiar with is heat energy. Heat energy results from the movement of particles within a sample of matter. Particles are continuously vibrating in matter, and when we raise the temperature of that piece of matter, the particle vibrations increase, therefore increasing the temperature. So what do you think? Is heat energy kinetic energy or is it potential energy? Well, that's right. Heat energy, because it's based on the movement of particles, is definitely kinetic energy. Now, what about chemical energy? First off, what do I mean by chemical energy in the first place? Well, we've seen actually a few examples of chemical energy in some of the photos that I was showing you. For example, when potassium was placed into water, we see that chemical energy was released. Here's another example, dynamite. Dynamite is made from a molecule called TNT, which stands for trinitrotoluene. Chemical energy is stored in the TNT molecules based on the position of the electrons around various atoms in the molecule. These electrons happen to be in a position of very high energy, and when TNT is ignited, those electrons can then move downhill, releasing all of that chemical energy. So what do you think? Is chemical energy an example of kinetic or potential energy? Well, that's right. Chemical energy is definitely potential energy. That's because chemical energy is based on the position of electrons in atoms and molecules. It's based on this position that those atoms and molecules are able to store chemical energy. And remember, when we're talking about potential energy, it's all about storage rather than movement. Let's talk about radiant energy. Radiant energy is also known as light or electromagnetic radiation. Light or electromagnetic radiation occurs when charges, being positive or negative charges, move through something called an electromagnetic field. So later in the course, we'll see light is emitted when electrons, which happen to be negatively charged, move through an electromagnetic field around an atom. So what do you think? Is radiant energy a form of kinetic or potential energy? That's correct. Because radiant energy is a form of energy that results from movement, we would best describe it as kinetic energy. What about nuclear energy? Nuclear energy is energy that is also stored inside atoms. Except instead of being stored based on the position of electrons, it's actually stored much deeper inside of the atom. In fact, it's stored in the smallest possible part of an atom, the nucleus. In fact, because the nucleus of an atom is so small and these forces are so great, the amount of energy that's stored there is immense. These energies are some of the most powerful in the universe. So what do you think? Is nuclear energy kinetic or potential? Well, that's right. Nuclear energy, being stored energy, is potential. And now we get to mechanical energy. Mechanical energy is energy at the macroscopic scale rather than the microscopic scale. It's based on movement and frictional forces. So, for example, when we have a train moving on a train track, there are a lot of mechanical forces happening down where the wheels meet the track. So, what do you think? Is mechanical energy kinetic or potential? Well, that's right. It's definitely based on movement, so therefore it's kinetic energy. And last but not least, we have electrical energy. We see electrical energy when we turn on a switch and a light bulb illuminates. In electrical energy, charges move through a medium. So is electrical energy kinetic or potential? That's correct. It's kinetic energy because it's based on movement of charge. Now, there's one more important aspect for us to discuss before we wrap up our introduction on energy, and that has to do with a particular type of energy, specifically heat energy. Because chemistry often involves the careful study of the way heat changes during the course of a chemical reaction, we have special terminology to refer to the way that heat is moving in or out of a reaction. These terms specifically are exo and endothermic. When we say that a process or chemical reaction is exothermic, what we mean is that the heat is exiting that system. When heat exits the system, we observe the heat moving out of the system as a temperature change. So if we have a process and it heats up, that means that process is exothermic. The term endothermic refers to a system that absorbs heat from its surroundings. In this case, because the process requires more energy than it has, energy flows inward. How would we recognize that we're dealing with an endothermic process? Well, that's correct. Its temperature would decrease as it proceeds forward. So let's think about two examples of exothermic and endothermic processes. Let's think about hot packs and cold packs. You can go to the grocery store and buy something called a hot pack. When you get this hot pack, the instructions will tell you how to activate it. Usually it involves crushing the thing up in some way. After you do that, it starts to warm up and eventually gets pretty hot. We would describe this as an exothermic process. There's a chemical reaction taking place inside of that hot pack that releases heat energy. Now you can also buy a cold pack. Cold packs, of course, get cold when you activate them. This is the result of endothermic chemical reactions taking place inside of the cold pack. So now we know what the terms exothermic and endothermic mean, and we're going to use those terms to further describe chemical reactions as we learn about them. And that brings us to the conclusion of Chapter 3. I hope you've enjoyed the lesson. Please let me know if you have any questions, and I will see you soon.